Good morning. In the first part of today's recitation video set, I'd like to talk about complex arithmetic and go over some examples in which we do a variety of mathematical operations on complex numbers. The first and most basic operation we can do with complex numbers is convert them from what's known as polar format into rectangular or Cartesian format. What I mean by this is to take the format of, let's say, a e to the j theta, which is known as the polar format for a complex number, and convert it into the form of x plus jy, which is known as the Cartesian or rectangular format. The reason for why it's known as the rectangular format is because if we take the x and y axes as being the real and imaginary parts of the complex number respectively, then we can basically plot any complex number on this 2D plane. So take the point here, for example, which I'm going to label x plus jy. The real component of this complex number is x, which can be represented by the coordinate as I've labeled it here. And the imaginary component would be labeled y, as I've done it here. So how do we convert to polar format? Well, polar format simply means that we're going to express this number now in terms of its magnitude and phase. And when we talk about the magnitude and phase, we're really referring to the vector from the origin to the point x plus jy. The magnitude would be the overall length of this vector. So I'll label it capital A. And the phase would be theta, or the angle from the positive x-axis up until this point. The conversion between these two numbers can be done by just considering trigonometry on this diagram. So for example, the magnitude A can be written in terms of the Pythagorean theorem by just taking the square root of the sum of the squares. So we would write that A equals the square root of x squared plus y squared. Conversely, we could find theta by just taking the tangent inverse of y divided by x. So this would be the arctangent of y, which is the imaginary component, divided by x, which is the real component. We can go the other way. In other words, given the polar format, we can go to the rectangular format by taking advantage of Euler's formula. Euler's formula is a relationship which relates e to the j theta to the Cartesian form by, again, using trigonometry. So if you think of the more general version of it, which would be a e to the j theta, we can write a e to the j theta as the sum of its real plus imaginary components. What is the real component? Well, it would just be the length of this segment here, which from trigonometry we could write as a cosine of theta. Then we would add to this the imaginary component, which would be y, and that is equal to the vertical side of this triangle here, which would be plus j times a sine theta. Euler's formula is just the version of this relationship where you have a unit magnitude. So if a equals 1, then we can write that a to the j theta equals cosine of theta plus j sine of theta. So in this way, we can find that x is equal to a cos theta and y is equal to a sine theta. Okay, and a lot of complex arithmetic just revolves around going back and forth between these conversions to make our life easier. So, for example, it's easier to add complex numbers when you're in the rectangular format. Let me give you an example. Suppose I had 2 plus 3j, and I wanted to add to this 4 plus j. To add two complex numbers together, you would just add together the real parts as well as the imaginary parts, and you would get, for example, 6 plus j4. So this is relatively easy. But if we wanted to divide or multiply, so this would be add or subtract actually, doesn't matter. But if you want to multiply or divide two complex numbers, this is much more easily done by using the polar format. Consider a e to the j theta divided by b e to the j phi. the magnitude of this division would just be the division of the magnitudes. So you would get a divided by b, and we would just subtract the exponents. So this would be e to the j theta minus phi. This is quite easy to do. Let's do some other examples to see how we can use these principles to make our life easier. Let's consider the number 1 minus 1 plus j square rooted. We can also write the square root operation by taking the power to the 1/2. This is our first example, so let me label this as example 1. And what I want to do is I want to express this number in both polar format as well as Cartesian format. Now, taking the square root is much more easily done in polar format, because if I have a complex number in general, which is a e to the j theta, and I want to take it to any power, I don't care what the power is, let's say to the power of n, then this would just be equal to a to the n times e to the j n theta. So the first thing that we need to do to simplify this number would be to convert the number minus 1 plus j into polar format. The magnitude would be the sum of the square of the real component and the imaginary component. So we would get minus 1 squared plus 1 squared as the magnitude of the number. And the angle of the number would be the tangent inverse of the imaginary component, which is 1, divided by the real component, which is minus 1. And then, of course, all of this, we then need to continue to square root. So we take it to the 1/2. Let's first simplify the expression we have in the middle here. So minus 1 squared is just 1, plus 1 squared gives us 2. So we have the square root of 2 times e to the, now let's think about what this tangent would be. This is where some of the standard triangles come in handy. So if you have a 1 and a 1, then this must be square root of 2, and this is the standard triangle you would get when you're at 45 degrees. So I can write this as e to the j minus 45 degrees. And of course, all of this then has to be square rooted. So this would be 2 to the 1/4, whatever that number comes out to be, times e to the j minus 45 degrees divided by 2, which would be 12.5. So this is the polar format for the number that we're seeking. How would we convert it to Cartesian or rectangular form? Well, we would keep the magnitude as it is, so this would be 2 to the 1/4, but we would write the e to the j theta as cos theta plus j sine theta. So this would be the cosine of minus 12.5 degrees plus j times the sine of minus 12.5 degrees. This can be found easily enough in the calculator, and then you could just multiply it with 2 to the 1/4. Again, something you can calculate in your calculator to reduce this into a decimal form. But this essentially now is our rectangular format. Let's do another example. Let's now suppose that we have two numbers. Let's call z1 equal to 6 minus j4, and let's call z2 equal to minus 2 plus 1j. And I'd like to calculate a number of things. First, let's calculate what the product of these two numbers would be, z1 times z2. Now, we can surely write this as 6 minus j4 times minus 2 plus j1, and we can multiply this out in rectangular format by just, multiplying each term. So you would get minus 12 plus j6 plus j8, and we would get minus j squared. Since j squared is minus 1, minus j squared would just be plus 1. And then we could combine terms again to get minus 11 plus j14. So this is one way of doing the product. The other way of doing the product could be to individually convert each one of these terms into polar form and then to multiply. So we would do this by taking the square root of 6 squared plus 4 squared e to the j. Now remember, we have to take the imaginary divided by the real, so this will be minus 4 divided by 6. And now we have to multiply this with the same conversion of the second factor. So this would be the square root of minus 2 squared is just 2 squared plus 1 squared, which is 1, times e to the j, again, imaginary component is 1, sorry, tangent inverse of the imaginary component, which is 1, divided by minus 2. And then we would combine terms. So you would end up getting the square root of, let's see, 36 plus 16 would give us 52. So this would be the square root of 52 times 4 plus 1, which is 5. And then we would add the exponents together. So this would be e to the j minus 4 divided by 6. I forgot the tangent inverse here. Let me correct my thing here. It's the tangent inverse in both cases, minus tangent inverse of 4 divided by 6. Sorry about that. Let's correct this. So this would be minus tangent inverse 4 divided by 6, whatever number that turns out to be, and then minus tangent inverse 1 divided by 2. And again, this is a number that you could calculate out, and you could verify that these numbers gave you something, you know, with round off errors, of course, but it would give you the same number that we got before. Suppose we now wanted to do the division of these two numbers. So let's take the division of z1 divided by z4, or z2, pardon me. This would now be equal to 6 minus j4 divided by minus 2 plus j1. If we wanted to do this division in Cartesian coordinates, we could. It's a little bit more involved, but let me show you the method for doing it. What we would do is we would multiply the numerator and denominator with the complex conjugate of the denominator. So if this is minus 2 plus j, we would multiply by minus 2 minus j. Why would we do this? If you multiply a number by its conjugate, then you're left with the magnitude of that number. So because then the cross terms would cancel out. But to not change the value of the number, we then have to multiply the numerator by the same factor, so that essentially we're multiplying by 1, which doesn't change the value of the number itself. And then you can go out and do all these multiplications and eventually reduce it to Cartesian form. Again, a method which I think is a little bit easier is to do this using the polar form. Given that in the previous problem we've already written this as a polar form, how would we do actually the division? Well, instead of multiplying the two magnitudes together, we would be dividing the magnitudes. So we'd get the square root of 52 divided by 5. So this is the square root of 52 divided by 5. And then instead of adding the two angles together, we would be subtracting them. So we would get e to the minus j tangent inverse 4 divided by 6. And then instead of, let's see, I took a negative sign here, so actually this needed to be plus. And then now instead of having plus tangent 1/2, we would have minus tangent 1/2, tangent inverse 1/2, pardon me. And so we're subtracting the two angles from each other. What if we had a little bit more of a composite situation where we had something like z1 divided by z1 minus z2? How would we go about doing that? Well, we can consider what the easiest way of doing the subtractions and the additions as well as the divisions are. So let's first write out by substituting what the values of these numbers are. So this would be 6 minus j4 divided by 6 minus j4 minus 2 plus j1. Addition is most easily done in Cartesian form. So let's first add these two together, the denominator I mean. So you get 6 divided by minus j4. And then this would become 8 minus j5. And now this reverts to basically the same thing where we did before, where if we wanted to divide them, you know, you could either multiply by the conjugate, or you could just find the magnitudes, take the ratios, and subtract the phases. So let's do it the second way around. This would be the square root of 36 plus 16 divided by 64 plus 25. And then this would be e to the j minus the tangent inverse of 4 divided by 6 minus the tangent inverse of 5 divided by 8. The reason for why these minus signs come out is because the imaginary components themselves are minus. But this is how you would then write this in polar format. And if you wanted to afterwards convert to Cartesian, then you can use Euler's rule to write the exponential as a cosine theta plus j sine theta. let's do a few more examples. Let's consider the following problem. Where we have now z equals to -8 plus j6. And now let's find what, for example, the magnitude square of this number would be. So the magnitude squared of z would be just the sum of the squares. So it would be -8 squared plus 6 squared. Let's see how we would write something else. Let's think about how we would write z squared. So z squared would be equal to -8 plus j to the 6 squared. So we can actually do the conversion, or if you can do the conversion to polar coordinates and then multiply the exponent by 2, or you can just do it out in Cartesian. Let's say we did it out in Cartesian. Then you would get -8 squared, which is 64, plus j6 squared. And then we would have the cross term, which is, let's see what it is. It's going to be 2 times the product of these two terms. So it's going to be -8 times 2 times j to the 6. So you can see that there is a little bit of a difference between first taking the magnitude and then squaring versus directly taking the magnitude and then squaring. I'm sorry, let me state that again. There's a difference between taking the magnitude of a number of squaring and just directly squaring the number. Let's say we now wanted to take 1 over z. So again, the easiest way of doing this, I think, is just to convert it to polar form, and then you just take negative of the phase. So if we wanted to take, let's first write what the value of z is, and then take the inverse of it. So the value of z would be, again, 8 squared plus 6 squared times e to the j. We have a negative sign here because there's a negative sign in the real term, but this would be 6 divided by 8. We put the sign up front. And then if we wanted to flip this, what would happen? We would take 1 over the amplitude. So this would be 1 over 8 squared plus 6 squared. And then we would reverse the sign of the phase. So this would be e to the j, now with a positive sign, tangent inverse of 6 divided by 8, if we want to find 1 over z. Similarly, if we want to find something like z to the -3, this is just 1 over z cubed. So we would just take our previous result and cube it. So this would be 1 over the square root of 8 squared plus 6 squared cubed. And then how do we cube the exponent? We multiply by 3. So it's now going to be e to the j 3 tangent inverse 6 divided by 8, if we wanted to write that. If we then wanted to, for example, find what the real component of this last result was, so let's say we want to find the real component of z to the -3, let's, what would we do? Well, let's first keep the magnitude as it is. So you'd have 1 over, well, basically this coefficient here, let me just rewrite it. We would have this term, 8 squared plus 6 squared, and I believe we had this cubed. And then this term we would write in terms of the cosine plus j sign, except that we're only interested in the real component. So we're only going to keep the cosine of the argument, which in this case would be 3 times, what is it? The tangent inverse of 6 divided by 8. And this would be the real component of our number. So I would hope that if you, once you start getting really comfortable doing operations in complex numbers, that some of the more composite calculations, like the following 2 examples, will hopefully, in time, will come easy to you. So for example, this is our 5th example. Sorry, our 4th example. Let's consider simplifying 5 e to the minus j of 30 degrees divided by 2 plus j, 3j minus j4. What would be the easiest way of simplifying this? Well, we have a division. So instead of taking the 5e to the minus j 30 degrees and converting it into Cartesian, I'm going to take the denominator and convert it into a polar form. So this is going to be 5e to the minus j 30 degrees. And this number here, the 2 plus 3j, is going to be written as 2 squared plus 3 squared e to the j tangent inverse of 3 divided by 2. And then we still have to subtract the j4. Let's now divide through these numbers. So the magnitude here is going to be 5 divided by 4 plus 9, which is going to be 13. So we have the square root of 13. And then we have, let me shorten the bar here. So this would be our magnitude. And then our phase term would be e to the minus j 30 minus j tangent inverse 3 divided by 2. And then we still have to subtract j to the 4th. Now, because subtraction is done most easily in Cartesian coordinates, I'm going to take this term, the first term here, and convert it into Cartesian. So to do that, we just apply Euler's rule. So this is going to become 5 times square root of 13 times the cosine of now whatever this angle is. Now notice that the expressions, oftentimes with complex numbers, start becoming increasingly large. So what I'd like to do to just kind of simplify the arithmetic is I'd like to define a new angle. Let me define phi as being 30 degrees plus the tangent inverse of 3 divided by 2, whatever that tangent inverse would be in degrees. And so then I'm going to write this as being then the cosine of, now remember the way I've defined the phase is that this is minus the definition of phi as I've written it here. So I'm going to write this as minus cosine of minus phi plus j sine of minus phi. And then all of this is going to be minus 4j. And now I can just add the real and the imaginary components. So if I take a look at what the real components would be, the real component would just be 5 square root of 13 times the cosine of phi. I can drop the negative sign because the sign of negative phi is the same as the sign of positive phi. With sine, however, the negative sign comes out. So this would then be minus j times 5 divided by the square root of 13 times the sine of phi, and then plus 4 when you take minus j as a parenthesis. So this is actually the answer to the problem, but in Cartesian coordinates. How would I convert this back to real coordinates? Again, redefining things is very helpful because ultimately you're going to know the value of phi and what these magnitudes are, and you can punch them into the calculator and get regular numbers. But when you're doing things on the exam, especially, it helps if instead of spending all of your time doing calculator arithmetic, just redefine some of these more complex terms with different variables and continue the variable names. Otherwise, you'll end up spending half your existence on the calculator, which is okay when you're doing homework. But for the test, I'd rather that you not worry too much about the calculator arithmetic. So what I'm trying to say is, let's define a new parameter, a, here, and a new parameter here called b, such that this number is actually a minus jb. Then you can write that the original expression we found can be written in terms of polar coordinates by just taking the square root of a squared plus b squared and e to the minus tangent inverse j times the tangent inverse of b divided by a. And you can leave your answer in this form and just write, where a is defined as what? 5 divided by square root of 13 times the cosine of phi. And then you would say b is equal to what? 5 divided by the square root of 13 times the sine of phi plus 4. And then, of course, you have to define phi. So you would write phi, and you would just remind me that you've already calculated it, and that phi is equal to 30 degrees plus the tangent inverse of 3 divided by 2. And now you've expressed your answer, but you've kind of avoided having to go through all of these calculations. If at the end of the day you really need those numbers, then now you just have a simple way where you have a sequence of numbers that you can calculate, punch it in your calculator, and do all of the calculations in one step at the end. The other reason for why I recommend this is because if you carry through these manipulations, it becomes a lot easier to check this work than if you just change the numbers all the time during the calculation. And then when you go back, it's hard to see if you've dropped a minus sign or if you forgot to square something or so forth. So just leaving all your calculations to the end, at least when I've been doing problems, has been something that has helped me to maintain accuracy. Also, a lot of times when we're solving things, we have the opportunity of programming. So this can be easily programmed into MATLAB or a calculator. So again, it improves your accuracy in terms of calculations. Let's do one more example, which is going to be kind of our example 4b here, where this time we want to simplify the expression minus 20 times the square root of root 45. Root 45. There should not be a degree sign here. I wrote this wrong. Pardon me. Let me fix this. This should be angle 45 degrees. This is just another one of the shorthands that I talked about in one of the previous videos for the polar format of the number. Let's multiply it with another number in Cartesian format, and then divide by a number in Cartesian format, and then add another complex number to it. So again, multiplication and division is most easily done in terms of polar format. So what I want to do is keep this number in the front in polar format, and I'm going to write it in the way that I'm a little bit more accustomed to seeing, which is the e to the j 45 degrees. I just want to emphasize that this notation is the same. Writing 20 angle 45 degrees is the same as writing 20 times e to the j 45 degrees. So this is my first number in polar format, and my second number, now I actually have to calculate the magnitude and phase. So this would be the square root of 3 squared plus 4 squared e to the minus j tangent inverse 4 divided by 3. It's the imaginary divided by the real component. In this case, the imaginary component has a minus sign, which is why I brought that out up front. And then divided it by, now I want to convert the denominator as well to a polar format so that I can do all of these multiplications and divisions in one step later on. So this will be the square root of 2 squared plus 1 squared e to the minus j tangent inverse of 1/2. Again, the imaginary component was negative, which is why it brings a negative sign in front of that. And I'm going to leave this second term as Cartesian because once I convert and do all these multiplications, I'm going to convert that product into a Cartesian format, and that will much more easily add into the 2 plus j. So let's now compress all of these amplitude and phase terms together. So this is going to be e to the j, oh, wait a minute, let's 20 times the square root of 9 plus 16 divided by the square root of 5. There's my magnitude. Notice that I did not put the minus sign up front. So I'd like to just have a side note about the minus sign, because the minus signs can always be added into the phase terms. It's much more typical to keep the magnitudes as being positive, although as long as you're consistent, there's no problem in leaving the negative sign there. But how does the negative sign add in? Well, remember that the negative sign is just a product with -1. Where is -1 on the real imaginary plane that I'm drawing here? Well, -1 is just this point here. So that corresponds to a number that has a magnitude of 1 times an angle of 180 degrees. So we can write this as e to the j 180. We can write this as e to the j minus 180, because you could go this way too if you wanted to. Or you could also write this as, if you wanted to use, instead of degrees, you could just write this as e to the j pi, or e to the j minus pi. All of these numbers here that I've written here are equal to -1, just as a sidebar. So if I write this as 180 degrees, what is 180 degrees plus 45 degrees? That is going to turn into e to the j, 180 plus 45 is 125. So I'm going to write this as 125 degrees. Okay, so this is the minus sign included with the e to the j 45. Then I have to take into account this second term here. So this will be minus the tangent inverse of 4 divided by 3. And then I have to take this number in the denominator up and subtract it. So this is a minus tangent inverse 1/2. When it comes up, it's going to turn into a plus tangent inverse 1/2. So now I have a plus tangent inverse 1/2. And this gives me, now in polar format, my entire number, which I then still have to add to 2 plus j. But I want to convert this back into, again, a Cartesian system so that I can add them together. And again, I'm going to use this example of just combining terms. So I can call this magnitude, let's say, capital A, and I can call this entire face term here phi. And if I do that, essentially the number I have is a e to the j phi plus 2 plus j. You know, where a and phi are defined as I've kind of indicated in the previous slide. And so let me just do this in general in terms of a and phi. So this is going to turn into a cosine phi plus j times a sine phi plus 2 plus j. And one important thing to realize is that when you write the number, you always group the real terms together and the imaginary terms together. So you would write this number as a cosine phi plus 2. Here's my real component. And then you would write this as plus j times a sine phi plus 1, which is now my imaginary component. And if you wanted to write your final answer again in terms of a polar format, again, what I would do is I would redefine numbers. I would define this real number as being little a, define your imaginary number as being little b. Again, you can just backtrack all these calculations at the end, but then you could write this final answer in terms of polar form as the square root of a squared plus b squared times e to the j tangent inverse b divided by a, okay? And it is more than fine when you're on the test to leave your answer in this form with a's and b's and so forth, as long as you make clear and you write out explicitly at the end kind of what your calculation chain is. That needs to be very clear. So you would have to write that where a equals capital A cosine phi plus 2, little b equals capital A sine phi plus 1, and then either draw a box around it or highlight it or something, but then you would have to write out what a equals to. So you would write a equals to blah, 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 phi equals to blah, 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 right? And then this whole entire thing now is your compacted answer. And I'm fine with you not going through and doing the rest of the calculator arithmetic on exams. Okay, you need to do it on homework, but on exams, again, that's just calculator arithmetic as far as I'm concerned. I'd rather that you spend your time on the actual circuit analysis. Okay, so this gives an initial summary of just some items having to do with complex arithmetic. The last point that I'd like to just note to you is the idea of equality of complex numbers when you think of things in terms of an equation. So suppose I gave you an equation where I said, you know, a plus 2j plus 3 equals 4 plus bj. And I asked you to find what a and b was in this equation. Okay. When you have a complex equation, this actually decomposes into two real equations because you have to equate the real components. So you equate the real terms for one equation, and you equate the imaginary terms in a second equation. So this equation to the top is actually two equations. The first equation would be for the real terms. So you would write that a plus 3 must equal to 4. And the second equation would be the imaginary terms. So you would write that 2 must equal b. And from here you can solve for b, just b equals 2. And then from here you can find that a has to be equal to plus 1, because 4 minus 3 equals to 1. Okay, so sometimes if you have to solve for unknowns when you're dealing with phasors, remembering this will come in handy. And so I just wanted to mention that to you as a kind of final note. If you have any questions about complex algebra, complex arithmetic, please let me know, and I'd be glad to try to step you through some more problems. There are problems that are in our textbook that you can also look at for getting more practice. Again, I highly encourage you to take a look at the Sataku PDF, since it also comes with a solutions manual. That's a very easily attainable kind of source of additional practice problems. And if you ever get stuck on any problem you find, of course, you can always just send me the problem and I'd be glad to meet with you over Zoom or try to reply to you in email to go over that problem with you to make sure that you feel comfortable with the mechanics around complex numbers. Have a great day. I'll see you all later. Take care. Bye-bye.